So using the formula for theta, okay, path difference divided by small d, y, path difference into capital D by small d. Tell me, at what distance and at what angular position, okay, means at what value of y and what value of theta do you see the first destructive interference happening? Means what are the linear position and angular position of A? Rishi, tell me what is the path difference at the point A? With what path difference do they arrive there?
Lambda by 2.
Lambda by 2, directly substitute that. So what is the angular position of A? Just write lambda by 2 in place of delta x. So it becomes lambda divided by 2d. Lambda by 2 divided by small d. Okay. And the y coordinate for A will be lambda capital D by 2 small d. In place of delta x, you substitute lambda by 2. Okay. So depending on the path difference with which the waves arrive at a particular point, you can tell what is the distance of that point from the point O. Okay. And let us discuss the names of these points also. O is the point which is on the perpendicular bisector of the two sources. Okay. We call O as the central maximum. Okay. O is called the central maximum. A, which is the first dark spot that you'll see, or the first minimum you will see, okay, from O is called the first minimum itself. You will find another point below O also. In fact, you will find another line below O. Where is this pattern? Yeah. So this is O. Above it, you see A, where there is a dark band forming. Similarly, below it also at the same distance, you will see a dark band forming. Okay. O is bright. And on either side of O, you will find two dark bands. Again, after the dark bands, if you continue moving along the screen, you will again find two bright bands and so on. Okay, I think it is better if we write here. Yeah, this point is O. O is called the central maximum. Then on either side of O, you will have the first minimum. Okay, the upper one and the lower one are both called the first minimum. Next, after the first minimum, you keep moving along the screen, you'll again come across maxima. Okay, O is called the central maximum. Numbering wise, O is given the number 0. It's the 0th maximum, you can say. Okay. Then the next maximum that you see on either side of O is called the first maxima. This is how the numbering is done. And you need to remember this also. Okay. Central maximum, the number is 0. On either side, you will have minima first. Those are called the first minima. After that, the maxima that you get are called the first maxima. Okay. Then you will have second minimum. And after that, you will have second maximum. And so on. Okay. So that is how the numbers are written. Right. So A is first minimum, B will be first maximum. Sometimes they call it as first secondary maximum. The central maximum is the primary maximum. All other maxima are called the secondary maxima. So B is the first secondary maximum. D is the second secondary maximum. Okay, all other bright bands that you see are called secondary maxima except the central one. Central one is the primary maximum. These names you'll have to remember. So A is the first minimum, B is the first maximum, and so on. Okay. So at A, the path difference is lambda by 2, B path difference is lambda. C path difference is 3 lambda by 2. At D path difference is 2 lambda. You get the sequence like that. Okay. So tell me, what is the angular position of the first maximum? Means for the point B, what will the angular position be? Delta x is lambda, so substitute directly and tell me quickly. Isha, how much is theta for the point B? In terms of lambda and small d, anyone? Are you all awake or you slept off?
Uh,
Okay.
lambda by d, sir.
That's all, lambda by d. So theta for the first maximum will be lambda divided by capital D, and y coordinate of the first maximum is lambda. Okay, wait. Why did I write capital D? Lambda by small d. Sorry. Theta for the first maximum is lambda by small d, and y coordinate is lambda capital D by small d. We just substitute delta x as lambda. That's all. Next, theta for the second maximum. See, for the second maximum, the path difference will be 2 lambda. Okay, second maximum is this point D on the screen. What will its angular position be? You just substitute delta x as 2 lambda. It becomes 2 lambda by small d. And y coordinate of the second maximum will be 2 lambda capital D by small d. Now, in YDSC, the actual experiment, the screen is kept at a significantly large distance from the sources compared to small d. Capital D will be very large compared to small d. Like how large is very large? See, small d is the distance between two sources, that is a few millimeters. Okay. Capital D will be in meters. So the ratio will be 1:100 times or more than that. Okay, much more than that actually. Why should capital D be kept so large? Okay. Simple idea. See, whether waves undergo constructive interference or destructive interference depends on the angle at which they are traveling. Okay. Now, if you bring the screen closer, maybe somewhere here, you will see the bright and dark spots forming very close to each other. Okay, you will see a maximum here, then a minimum here, then again a maximum, and then minimum. The pattern of bright and dark bands will form very closely, and you will not be able to observe the clear difference between each band. The bands will be overlapping. Okay. Not overlapping, okay, they don't actually overlap, but bands will be very narrow. You won't be able to observe the pattern clearly. As you take the screen away from the sources, okay, you yourself can observe that the distance between successive maxima increases as the screen is taken away from the sources. So to be able to see the pattern of bands clearly, the screen should be placed at a significant distance from the sources. And mathematically also you can show here, see, the y coordinate of the first maximum is lambda capital D by small d. Now lambda is only one wavelength. Okay, that is about 400, let's say red color is being used, 700 nanometers. That is 7 into 10 power minus 7 meters. Now, small d is the distance between the sources. Distance between the sources is kept quite small. Okay, maybe 1 millimeter. 1 millimeter is 10 power minus 3 meters. The ratio of lambda by d is still 10 power minus 4. Okay, so capital D should be quite large. I mean, it should at least be something like, how much shall we take? Suppose you take capital D as 1 meter. Okay, the distance between the sources and the screen Let's say it is taken as 1 meter. Still, the ratio is 10 power minus 4. That means the y coordinate of the first maximum is 1/10 of a millimeter. That is very close. Central maximum is a dark band. At just 1/10 of a millimeter, you have a bright band. So the pattern won't be that clear. Suppose you make D as 10 meters. Okay. Place the screen 10 meters away from the sources. Then 10 into 10 power minus 4. The y coordinate of the first maximum becomes 10 power minus 3 meters, 1 millimeter. You will be able to see at least one, you'll be able to see the lines clearly then. And the greater you increase capital D2, okay, the wider the bands will be and the better the pattern will be visible. But there's another problem. If you take the screen very far away from the sources, the brightness won't be sufficient. Obviously, when you go far from a source of light, the brightness will decrease. Okay. So there has to be a balance. The pattern should be clear. The brightness also should be sufficient. In fact, the sources should be very bright actually. And you should conduct the experiment in a dark room. Then you will be able to see the pattern clearly. Okay. So I'm just explaining the reason why capital D is very large compared to small d, just for proper visibility of the pattern. Okay. So theta for first maximum, second maximum, similarly y coordinates we got. We can generalize this for the nth maximum. Angular position of the nth maximum. See, first maximum path difference was lambda. Second maximum path difference was 2 lambda. Similarly, if you continue that sequence, nth maximum path difference will be n lambda divided by capital D. That is the angular position of the nth maximum. Okay, I'll tell you why angular position is important. Next, linear position. You continue this sequence. Y coordinate of the nth maximum, you will get it as n lambda capital D by small d. But see, these are all, for NCRT or basic YDSC questions, these formulas will work. They won't work in other cases where the sources are not in phase with each other. In that case, these formulas are not applicable. Only if the sources oscillate exactly in phase, then the point O, the point on their perpendicular bisector will be a central maximum. If there is a phase difference between sources, O will not even be a central maximum. I mean, that perpendicular line won't be central maximum. Okay, it will change. We'll discuss all that. For now, we are dealing with cases where sources are in phase with each other. Okay. Now, what is the purpose of this nth maximum angular position? Okay, why don't we just find out the linear position? Okay, let me copy paste the pattern again. Let's use this one. Now see, we have marked a point P here on the screen, which is at a certain angle with the reference line. So theta is the angular position of P, and this distance is the y coordinate of P. Fine. Now, even if the screen is brought closer, okay, or taken farther, the same kind of interference will happen at this point, and you extend this wave or this line at this point. At these 3 points, okay, let me mark them in yellow. The same kind of interference will take place. What I mean is, suppose P is the third maximum. Okay, means you are getting a bright band here. Then even if you bring the screen closer, at that angle on the screen, you will see the same bright band. Right? So when the screen is brought closer or farther, the angular position of the maxima and minima does not change. The angle at which the waves undergo a particular kind of interference does not change. If they are undergoing constructive interference at that angle, they'll continue to undergo constructive interference at that angle, always. Okay. The linear position may change. Y can change depending on where the screen is placed. Theta will not change. Okay. That is why the angular position is important. It's something which gives you the definite pattern. Okay. Even if you change the shape of the screen, okay, sometimes you will be asked questions where the screen is circular in shape, like this, with its center as the midpoint of the sources. They'll ask you how many maxima minima will form or where the maxima minima will form and such thing. So if you know the angular position only, you'll be able to answer, because circular screen is not at a fixed distance from the sources. Fine. From one source, one point on the screen, maybe closer, another point will be farther. It's not like a flat screen. So that y coordinate formula won't work for a curved screen like this. Okay. Theta formula will always work. So you need to you need to know how to derive the angular position of any point where a particular type of interference happens, okay, where a particular path difference arises. Fine. Next is something called, okay, wait, we wrote formula for nth maximum. We'll also write for nth minimum. The first minimum occurs at point A, at which the path difference is lambda by 2. Next minimum occurs at point C, at which the path difference is 3 lambda by 2. The third minimum will be at point E, where the path difference is 5 lambda by 2, and so on. Okay. Basically, destructive interference has to happen. So angular position of the first minimum, okay, we'll do this quickly. Path difference is lambda by 2. So it is lambda divided by 2 small d. And y coordinate of the first minimum is lambda capital D by 2 small d. Next, angular position of second minimum will be 3 lambda by 2 small d. Y coordinate of second minimum 3 lambda capital D by 2 small d, and so on. We can generalize this. You can see that angular positions of minima are odd multiples of lambda by 2d. Okay, 1 lambda by 2d, 3 lambda by 2d, next will be 5, and so on. So if we generalize that pattern, okay, that sequence, angular position of nth minimum, can one of you tell me what the general term will be? 1, 3, 5, 7, and so on. How do we generalize this series?
2n plus 1 pi by 2d.
If it is 2n plus 1, substitute n as 1, it becomes 3. So it indicates that first minimum is at 3 lambda by 2d. It's not 2n plus 1. What is the other way to write a series of odd multiples? What I'm saying is, if you take the general term as 2n plus 1 lambda by 2d, then the first minimum, if you substitute n as 1, arises, not arises, the first minimum occurs at 3 lambda by 2d according to this formula, which is not correct. Okay. Yeah, the correct way to write it is 2n minus 1. 2n minus 1 lambda by 2d. Then you put n as 1. 2 minus 1, you'll get lambda by 2d. If you put n as 2, 2 into 2, 4 minus 1, 3 lambda by 2d. And so on. It will fit the sequence correctly. And y coordinate of the nth minimum in YDSC will be 2n minus 1 lambda capital D by 2d. Fine. As I said, you'll use these to answer basic questions based on YDSC where the sources are in phase with each other. Pradyun is asking, 2n plus 1 can work from n is equal to 0. But see, we want the distance of the nth maximum, no, or nth minimum. Okay. If you put 0, you get, I mean, if you substitute n as 0, you'll get lambda by 2d. No, it won't. Okay, in 2n plus 1. In 2n plus 1, lambda by 2d, you put n as 0, you get lambda by 2d. But that will mean 0th minimum. Okay, substituting n as 0 means you are looking for the 0th minimum. There's nothing like the 0th minimum at all. Okay, first minimum will be there, then second minimum will be there. So you will start, the numbers start from 1. Fine. So you cannot substitute 0 there. So you use 2n minus 1 lambda by 2d. Fine. Next is something called fringe width. What is a fringe? Basically, each band that you see on the screen is called a fringe. Okay, in this pattern, the bands are called fringes, and the width of each band is what you call as fringe width. So mathematically, you can say fringe width is the distance between one minimum and the next minimum. This is one fringe. This is one fringe. Okay, these are all bright fringes that I am highlighting. Okay. So in YDSC pattern, okay, interference pattern, we get the maximum at lambda by, okay, y coordinates, if you see, lambda capital D by small d, next is 2 lambda capital D by small d, and so on. So the y coordinate of this central maximum is 0. Y coordinate of the first maximum is lambda capital D by small d. Y coordinate of the second maximum is 2 lambda capital D by small d. Third maximum will be 3 lambda capital D by small d, and so on. Okay. What is the distance between two bright bands? For example, if you take these two, first maximum and second maximum, the distance between them is lambda capital D by small d. Similarly, the distance between the central one and the first one is also lambda capital D by small d. So the distance between successive bright bands or bright spots is lambda capital D by small d. Same will be the distance between successive dark bands or dark spots. And that is what we call as fringe width. Therefore, in YDSC, the fringe width, you can call it W, is equal to lambda capital D by small d. And we see that all the fringes will have the same width. You see a pattern with uniform fringe width. Okay. But there is a condition for this. When will you get a uniform fringe width? When will all fringes be of the same width? When theta is very small. Because you are using this formula lambda capital D by small d. This formula lambda capital D by small d for the y coordinates, or this formula delta x capital D by small d, is valid only when the angles at which you see the bright and dark bands are very small. Okay. Only when theta is a very small angle, you get this formula for y coordinate. Okay. In fact, for angular position also, delta x by d is applicable only when theta is very small. Otherwise, this is the actual formula that you are supposed to use. Sometimes they ask questions based on this also. They give you a large angle, okay, or that ratio delta x by d will be a large value, and they'll ask you at what angle you will get the first maximum or what kind of interference happens at that angle. Okay. So remember, theta is equal to delta x by small d and y is delta x capital D by small d are both valid under small angle approximation. Now the fringe width formula is being derived based on that. Okay, lambda capital D by small d. So in YDSC pattern, in like actually when you conduct the experiment, yes, the angles will be small and the pattern that you see will be a pattern of uniform fringes. But in problems, If they want to trouble you, they can change it. Okay. Let's solve one problem based on this. I'm telling you beforehand, you can't use this formula of fringe width, okay, to answer this question. So suppose the distance small d between the sources is, let's say 4 lambda. Or, okay, let's take 2 lambda itself. Distance between the sources is 2 lambda. That means at any point away from the two sources, the maximum possible path difference itself is 2 lambda. You can't get path difference more than that. And that 2 lambda also, where will it occur? Like if you consider two sources like this, the distance between the sources, if you take it as small d, then when you consider waves traveling almost parallel to the line connecting the two sources. Okay, if you consider one wave from S1 like this and one wave from S2 like this, traveling in almost the same direction, then at such points, if they interfere, okay, then you can see that the distance traveled by the wave from S1 and the distance traveled by the wave from S2, they arrive there with a path difference of small d. Okay. So for path difference to actually be equal to the distance between the sources, the angular position will have to become 90 degrees. Okay. Because sine theta is delta x divided by d. We want delta x to become equal to the, or fine, let us think of it in the reverse way. For this or anywhere along this direction, the angular position is 0. Anywhere along this direction, maybe the angular position is 30 degrees. Along this direction, 60 degrees. Along this direction, the angular position is 90 degrees. When angular position is 90 degrees, this becomes 1. That is when you get path difference equal to the distance between the sources. In any other case, sine theta will be less than 1. Path difference will be less than small d. Okay. So this is mathematical proof that the maximum path difference is the distance between the sources. Okay. So consider two sources which are placed at a distance of 2 lambda from each other. Let's say the screen is placed at a distance, okay, this is 2 lambda. Assume the screen is at a distance of 4 lambda from the sources. Sources are in phase with each other. Their wavelengths are equal, amplitudes are equal, all that is fine. Find out the angular position and the linear position of the first maximum. One of you quickly tell me, what is the path difference with which they interfere at the first maximum? What is the path difference with which waves must interfere at the first maximum? Okay, let's say these are the sources. At a small distance from the sources, there is the screen. The point on the screen, which is on the perpendicular bisector of the sources, becomes the central maximum because the waves from S1 and the waves from S2 travel equal distances to arrive at O. Therefore, the path difference becomes 0, which means phase difference is 0, which means they undergo constructive interference, and that becomes a maximum. The next maximum will be, as you move away from the point O, the next maximum may occur somewhere here. That is what you call as first maximum. Obviously, the waves arriving there travel different distances. Okay, so they arrive there with some path difference. Let the path difference be, for constructive interference to happen, the path difference should be lambda. Then the phase difference will be 2 pi, which will again correspond to a maximum. That is what we call as first maximum. Okay, you need to understand how these maxima and minima are forming. What I asked you to calculate in this problem is this distance and okay, this angle. Okay, instead of 4 lambda, capital D, 4 lambda, let's take capital D as a large value itself. Assume it is some, okay, 100 times the wavelength. Okay, so the screen is placed quite far from the sources. Find out the angular position and the linear position of the first maximum. Try this, both of you. I'll give you 2 minutes. Listen, the distance between the sources is just twice the wavelength. So you can't expect to see the maximum or the bright band at a small angle. So small angle approximation won't be valid here. Let's go back to the diagram using which we derived the formula for theta. We did this in the last class. You go through the video once, it will be clear. So we consider one source from S1, one wave from source S1 arriving at a point P on the screen, okay, like this. And we consider one wave from the source S2 arriving at the same point P on the screen. Now, if the screen is quite far from the sources, quite far means compared to distance between the sources, it should be far. If the screen is far enough, the point P will also be far from the sources compared to the distance between them. Mathematically, if you take a point which is far from two other points, okay, so P is far from S1 and S2. If you take such a point and you draw lines from S1 to P and S2 to P, the extra distance traveled by the wave from one of the sources compared to the other can be derived using this triangle. From S1 to, from S1, to the wave traveling from S2, you drop a perpendicular first. Okay, that blue line that I have just drawn. Then the distance between the sources, that perpendicular, and this extra distance traveled from S2, they will form a right angle triangle. Rishi, is that clear?
Yes, sir.
So in that right angle triangle, the angle at the top, the angle near S1 will be theta, where theta is the angular position of the point P. Okay, all simple geometry only. If point P's angular position is theta, then the angle in that triangle will also be theta itself. Then apply simple trigonometry for that triangle. Sin theta becomes opposite side, the path difference, divided by hypotenuse, the actual distance between the sources. That's all. This is the proper formula for the angular position at which you expect a certain path difference. Is this clear?
Yes, sir.
So sin theta is delta x by d. Remember this. Now, what were you asked in this problem? You were asked to find out the angular position theta and the actual position y of the first maximum. Now, we already discussed what happens at the first maximum. The path difference expected is lambda. So just substitute that in the formula. What was the formula for sin theta?
Delta xy small.
That's all. Sin theta is delta x divided by small d. We want to know that the theta value at which path difference is lambda. Okay, I didn't tell you that in the question directly. I called it as first maximum, but you should understand that first maximum corresponds to path difference of one wavelength. Okay. And what was the distance between the sources given to you? 2 lambda. So this becomes 1 by 2. Sine of what angle is 1 by 2?
Sine 30.
30 degrees. Correct. So that is the position at which you find the first maximum. And once you know theta as 30 degrees, and you know this distance is 100 lambda, 100 times the wavelength, can you find out y? Can you calculate y? You just need to use this right angle triangle now. We got the angular position as 30 degrees, and we know the distance adjacent to that angle, 100 lambda. We need the distance opposite to that angle. How will you relate them? How are theta, y, and capital D related? In a right angle triangle, how do you relate opposite side and adjacent side? You use tan theta. Opposite is y, adjacent is D. Simple. We found that theta is 30 degrees here. Therefore, tan 30 degrees should be y coordinate of the first maximum divided by the distance between the sources and the screen. Distance between sources and screen is given 100 lambda. Therefore, y coordinate of the first maximum will be 100 lambda into tan 30. Tan 30 is 1 by root 3. That's all. So even if the small angle approximation is not valid, you can tell what is the distance at which you can find the maximum and minimum. Clear? Fine. Suppose the distance between the sources is, say, 4 lambda, and distance between sources and the screen, let's say some 200 lambda, or you can take it quite far away, let's say 1000 lambda. Find out the angular position, or Rishi, try to tell me, if the distance between the sources is 4 lambda, how many maxima can you see on the screen?
4.
How did you say it is 4? See, where do the maxima form, or what should happen at a maximum in terms of interference? What kind of interference should happen? Maxima correspond to points where constructive interference occurs. Okay. And for constructive interference, the path difference should either be 0 or lambda in terms of wavelength, lambda or 2 lambda, and so on. Okay. You should have these path differences to be able to see a maximum. At the central maximum means on the perpendicular bisector of the sources, you get path difference 0. As you go away from the perpendicular bisector, the path difference can become lambda, 2 lambda, and so on. But the maximum value of path difference possible is the distance between the sources. So you can have path differences of, like in this case, if the sources are separated by 4 lambda, you can have path differences of 0 possible, lambda possible, 2 lambda possible, 3 lambda is possible, 4 lambda is also possible, but that occurs at infinity, infinite distance on the screen. And at each of these path differences, you will get a maximum. So this will give you one band, this will give you a second band, third, fourth, fifth. But the thing you need to remember is you will see dark and bright bands on the upper side of central maximum and also on the lower side of central maximum. Okay. The point where path difference is 0 will be 1 point only. Okay. That point O, where the path difference is 0, will be only one, will occur only once. But the point where the path difference is lambda will occur twice. Once above O and once below O. The point where the path difference is 2 lambda will also occur twice if the screen is long enough on both sides. Okay, we are assuming an infinitely large screen. So you will see 0 path difference at one point, path difference of lambda at 2 points, path difference of 2 lambda at 2 points on the screen, and so on. Okay. So 0 will be only 1, but you'll have 2 of these, 2 of these, 2 of these, and 2 of these. So totally how many bands will form? 4 twos is 8 plus 1, 9 maxima will form. Is this clear?
Yes, sir.
Okay, we can visualize also. Suppose these are the sources. And okay, I like in the question I have given the screen to be quite far from the sources, 1000 times lambda. Let's say it is like this. So on their perpendicular bisector, the path difference is 0. Then at a particular point on either side of that perpendicular bisector, you will see waves arriving with a path difference lambda. This is one, and this is one. So you call this as, like, if the path difference here is lambda, you call this as the first maximum on the upper side. And here the path difference is lambda. You call this as the first maximum on the lower side. Both are first maximum only. Okay. So you will have two of each maxima other than the central one. Central will only be one always. Okay. The other maxima will occur in pairs. Other minima also will occur in pairs. Okay. Fine. We'll stop it here for now. Next class, we will look at how the actual YDIC experiment is conducted and what if we make some small changes in the experimental setup, what will happen to the pattern. Okay, all that we will discuss. So basically, this is the idea that Young proposed, okay, to check the wave nature of light. If S1, S2 are two sources of waves, then when you place the screen at a certain distance, you should see a pattern. If the sources are coherent, you should see a pattern on the screen. So Young wanted to try that. He wanted to take two sources of light, 2 point sources of light, place a screen from them at a certain distance from them, and look for the pattern. But how do we create two sources of light which are coherent? First of all, coherent means they should have the same frequency. Only then you will get the pattern. Okay. How to get coherent sources of light? How to ensure they are in phase with each other? All that we will discuss in the next class.